Yes. Okay, Infi 2, lecture 7. Oh my God. Already 7. I want to mention you the area function we saw last lecture. If you want to turn the light something, it's fine from me. I don't need it. We saw that the area function of an integrable function f in a segment AB is defined by s of x is the integral from a to x of ft dt. Let's move the cursor away. We stated two main things about S, while the main theorem from lecture number 6 was the corollary from the theorems that we can use the antiderivative, the big F, for calculating the integral. Now I want to focus on the two main things we said about S itself. First of all, we said that, first of all, S is continuous. And secondly, if F is continuous, then S is differentiable, and we have the derivative of S is F. And more explicitly, that's what I want to write down right now. The derivative of the integral from some constant a to x is the function inside the integral, which we call the integrand, if you want. It sounds Spanish somehow. The integral. Integrand. Integrand. If you want to refer with the, yeah, if you want to refer to the function inside integral and while looking and sounding so sophisticated, you can call it the integrand. I don't call it like that myself, but that's the term. And now, what do I want to do today? First of all, it's not written down correctly. Continuous. Yeah. What I want to do is focus on this equation, which technically means that we know how to derivate, whatever, an integral. Now, there are a lot of mathematical, practical problems that requires derivative. For example, that's kind of example I'm going to do here, but it's not the only one. We want to calculate some limit, and in order to do so, we need to use L'Hopital theorem, which requires us to find derivative. And if we want to calculate some limit of containing an integral, we can do it. So right now, we know how to find derivative of integral. Another example on that kind of questions is finding extremas, finding extrema points. We can find the derivative of the integral, and then it is equal to 0 and find the points of extrema. Another example, if we want to show that a function is monotone, strictly increasing or strictly decreasing, we can show that the derivative is always positive or always negative. And we now know how to do it when it comes to integrals as well. I want to write down in one sentence, then have an example. So now we basically know how to derive or derivate, right? Finding the derivative. Derive was derive an integral. For example, um, let's. It is 7, right? It's already 7. We let's find together. Let's find the limit lim where x tends to 0 of, it will be, the limits will be not actually under and over the integral, but more to the sides because it is in the numerator. I can help it though if I write it down that way. A number you like? 7. Okay. Another one? No, I will use 7, but I need that one. 11. 11. 7, 11. It's good. X to the power of 7, 11, and it is multiplied by the integral from 0, doesn't actually matter. X sinus of t to the power of 6 dt. I want to calculate this limit. It is, of course, a limit of a fraction, which already smells like L'Hopital. But before we apply L'Hopital, and then we demonstrate how to derive an integral, we need to make sure that both the numerator and the denominator goes to 0 or to infinity. Now, the denominator goes to 0, 11 x to the power of 7 when x goes to 0. It is very simple. Why does the integral goes to 0? Now, the denominator and numerator both go to 0. The denominator is trivial, but the numerator, we know that s, meaning the integral, is a continuous function. Because s is a continuous function, we have that Sx goes to s of 0. And s of 0 is the integral from 0 to 0. You know, from 0 to hero, from Hercules. Yeah, it's a good song. I don't know if you're familiar with the Hebrew version of it, but the translator, whoever he is, who translated the songs to Hebrew, used a very high level Hebrew for the songs, which is extremely funny. It's like, you know, the characters go and talk to each other, and then they start singing, boom, it's a verse from the Bible. Which X in this case is a constant or variable? Is a variable. It's the upper limit of the integral. Oh, wait, we didn't do it. No, it's just in the limits of the boundaries of the integral. So SFS is 0 is the integral from 0 to 0, which is 0. Reminder from Sunday, the integral from one point to itself, be it 1 or 12 or 0, is 0. So the numerator goes to 0 as well by the fact that S is continuous. And now we can use L'Hopital. So we can use L'Hopital. It's without all the fancy schminglings above and under the letters. It's French, probably has some tag on the A or something. We can use L'Hopital theorem or L'Hopital rule. The limit is the limit where we derive both the numerator and the denominator. And now, by our theorem, we called it the first part of the fundamental theorem of the calculus, we know that the derivative of the integral is the function inside the integral. We switch the letters. Instead of t, we can now write down x because we are no longer of need of 2 letters because the integral is gone. Yeah. Okay. I'll try my best. I'll keep going. So it's 77 x to the power of 6. And right now, one can, first of all, apply L'Hopital for a second time and get the answer. Another way, probably more convenient, is to take the 77 outside and look at the limit of what's left. The limit of what's left is one of the notorious limits of infi 1. When you have sinus of something above the something and the something goes to 0, the limit is 1. Is Erez gave a spatial name to the limit or just no?
He just gave it in the exam and no one got it.
No, me neither, but I'm teaching math as well at the College of Management in Rishon LeZion, and there they call it the amazing limit, not the amazing, wondrous, I don't know, something like that, something very fancy. And unhinged. What?
In Hebrew, how do they call it?
They call it the הגבול המופלא.
Ah.
Yeah, the amazing.
I mean, surprising, maybe.
Surprising is מפתיע. The amazing Spider-Man is translated to Spider-Man מופלא. So it be the amazing limit. Which is which is funny. So by L'Hopital rule, L'Hopital's rule, yeah, with the S. The limit is 1 above 77. Yeah, the question?
If you try to take the integral from 0 to 0 of 1 over x,
Yeah.
what would that be?
First of all, by definition,
Oh,
the integral above 1 point is 0, no matter what, because it doesn't have any area beneath it. But talking about functions that are not bounded in the segment we want to calculate integral is a discussion we're going to have next week. Yeah, here we started the discussion about definite integral in lecture number 4, or even in the end of lecture number 3. And today, lecture number 7, we are going to finish the discussion. Lecture number 8, we start talking about integrals of functions that are not bounded, or the integral is over in some infinite segment, etc.
you replace it with variable and take the
Yeah. Yeah, you did things, very impressive things in high school. In Israel, we're not never.
I did like next to math course.
What? Impressive. Any other questions? So I want to have a note or something like that. What are we going to do? What can we do against such reckless fate? What can we do when the limits of the integral, the boundaries of the integral are not just a and x, I mean a constant at x, but some but more complicated expressions. It's 2s or 1s expressions. I think it's for example, and again, the motivation is I want to calculate the limit using L'Hopital theorem. I want to find the extrema points. I want to prove that the function is increasing. So I want to show that the derivative is not negative, etc., etc. I need to find derivative, and we talk about an integral. So for example, let's say I want to find the derivative of the integral between x squared and square root of x, just for example, of the function cosinus of t to the power of 4. Just for example. I want to find the derivative of that. How do we do it? Generally speaking, talking about an integral, or finding the derivative of an integral, that its boundaries are themselves functions of x, not just constant in x, but some functions of x. How do we do that? Now, the question, why do we do that? Besides, it may appear in the final exam, so we need to know that. Is again, we want to answer some question that requires a derivative about an integral. Limit, extrema, monotone function, as I mentioned, and you can think of different kinds of examples yourself. So how do we do it? In the bottom line, we're going to have some formula, and it won't be very complicated, but I don't, me myself, I don't remember the formula right away. Probably I do remember it, but it's because I teach it every semester more than one time. I teach it, I taught it, taught, I say taught it in the morning to the Hebrew group, Hebrew class, and now I'm teaching you as well. But what you need to remember is the properties of definite integral we use in order to calculate this derivative. How do we do it? Okay. We know that Sx is the integral from some point A. One can choose if you want 0, something like that, of f. So we can write the integral from g to h in the following way. First of all, stick with we've already done more than one time on Sunday. The integral between g and h is actually the difference between two integrals. The integral from, for example, 0 or a, for some a, whatever, of f, and the integral from a to g. When we subtract that integral from this integral, we are left with the integral between g and h, as we mentioned on Sunday. And now, s of x is the integral from a to x. So what is the integral from a to hx? Is s of hx. And the integral from a to g is s of g. Now, let's write it down normally. And we know how to derive that. We get the derivative of the general integral, no, is the derivative of the difference between these two s's. Now derive a function with another function inside it. We call it the chain rule. Is derivative of s at h multiplied by the derivative of h, and the same with g. But the derivative of s is f. That's what the first part of the fundamental theorem states. So we can write it down as f at h multiplied by the derivative of h. It won't go in one line, so I write it down as another line. Minus f at g multiplied by the derivative of g. So if you generally want to, and I write an example right away, if we generally want to find the derivative of an integral between g and h, not just a and x, but some other expressions of x, we can do so. And this is our bottom line. Let's write this example here.
Why do we find the no,
What?
We're trying to find derivatives with integrals.
Yeah.
How do we integrate them with normal? Like, if we have these functions,
Oh, that's
what they're trying to do.
that's the no, that's a good point, because let's say I want to again find this derivative. Now here, when it's cosinus of t to the power of 4, we don't know how to find the antiderivative. We don't know how to calculate the integral, write it down as an elementary function.
We don't
We don't at all. Yes, cosinus t to the power of 4, just like e to the power of x squared, or sinus to the power of sinus of t to the power of 3, or something like that. They do not have an elementary antiderivative, big F. We don't know how to write this down with some big F. And the whole point of the theorem that we are looking at it now, we don't need to find the big F and write it down. And I told to the Hebrew students in the morning, a nice tricky question would be something with a function that we can find the antiderivative, the big F, but it will take much longer than using the theorem itself. So any student who don't know how to use the theorem will have to work very hard in order to find the integral and then calculate the derivative of what he gets. But when we can use the theorem and how we generally write it down here, it will be very easy. In this example here, f is the cosinus t4, and h is the upper limit, which is square root of x, and g is x squared. So f of h, plugging in square root of x instead of t, gives you cosinus square root of t to the power of 4, which is x to the power of 2. F, you plug in g. Instead of t, we put x squared, so it is x to the power of 8. And the derivatives of h and g are 1 above 2 square roots of x and 2x correspondingly. And so by our theorem, the derivative of the integral is that, which gives us in this specific case cosinus of x squared multiplied by 1 above 2 square root of x minus cosinus x to the power of 8 multiplied by 2x. Now, this expression specifically is a bit complicated. I mean, if I want to say, yeah, it's always positive, so the integral is an increasing function, it will be problematic. Depends on what x and what the segment you're looking at, of course. But for different examples, we can get some more nicer expression that we can discuss further on. Okay, it's always positive. I want to find when it is 0 to calculate the extrema points, etc., etc. So this is how we find the derivative of an integral, generally speaking, not just from a to x, but between 2 points of two expressions, sorry, of x, whatever these expressions are. Of course, there is a secret assumption here that all the functions f is continuous, so s is differentiable, and g and h are differentiable. And we wrote down the derivatives of them. Yeah. Yeah.
Why doesn't the derivative and the integral cancel out?
They cancel out. That's what basically our theorem states, only when the limits, the boundaries are a constant and x. Now, when the boundaries are different, we have to pay the price, the collateral damage of h tag and g tag. And x. Yes. Yes. If g was a constant, so derivative is 0, and this is all 0, but h was some function, some expression of x, we still had f hx multiplied with h tag, and not just f. Because thinking of an integral as the opposite of the yin to the derivative yang, it's thinking about the antiderivative, about the indefinite integral. And as we know, the indefinite integral, the antiderivative, and the definite integral are connected through our main Newton-Leibniz theorem of FB minus FA. But as we emphasized Sunday, they are not the same exactly. Yes, in high school, everything works fine. Derivatives, I don't know yet again what you actually have learned, but here in Israel, we don't talk in high school about points where the function is not differentiable, for example. So it's always working. So here it is not always working, yeah.
That you just had the integral of like keeping the root of x and x squared, that thing, and it was just sine the inside. How do you introduce that?
If it was just, let's, for example, if it was only cosinus t,
Yeah.
which is a function that we are familiar with its antiderivative. The antiderivative of cosinus is sinus. Yeah. If it's minus sinus and I'm wrong, correct me. And then I should plug in t as x squared as the bottom boundary, and as the upper one, t is square root of x. And this is going to be sinus of square root of x minus sinus of x squared. Now, if we know, and it is easy, finding that derivative, we can find it and then derive it regularly. I mean, not theorem, not at all. But here in our question, first of all, it was cosinus t to the power 4. And as I mentioned, a nice sticky question would be, I mean, here we cannot find that derivative, so we must use the theorem. And it won't work, because the price you pay for the dt will appear in the denominator and it will be uglier. Cosinus t above some t power 3 or something. So it's somehow easier because right away we know that we cannot find an antiderivative, so we must use this, the theorem of how to derive an integral. And on the other hand, when the function is very simple, just cosinus t, we can easily find the antiderivative and just derive it with our derivation rules. The nice questions are a function that we can find its antiderivative, but it is complicated. So you can do it both ways, using a theorem or finding the antiderivative explicitly and then derive it. But it will be much harder finding it. It will be much easier using the theorem. Okay. Any other questions? So now I want to move on and maybe near, don't know if in the last practice, which is Sunday, but probably in the next practice, we'll go through it more thoroughly, I know, and homework as well, and some geometric just like that, geometric use properties, aspects, don't know what I actually want to say, aspects of the definite integral. First of all, the basic one, I believe, who is it?
And from
Come sit with us, it's free. Is he Jewish?
Yes.
So tell him it's free.
It's free.
Um, we all know, doesn't matter which high school we went and had fun, that the integral is used to calculate the area. Now, by our very nice definition, it is the signed area, which means the area beneath the x-axis is considered negative, and you can cancel the positive area, etc. etc. We talked about it in lecture 4 already, and maybe even in lecture 3, I don't remember correctly. Now, we know that generally speaking, from high school, so I don't want to talk about it much. High school, if f and g are both integrable function in the segment A to B, the area, in Hebrew I say trapped, לחוד, כלוא, whatever, jailed, imprisoned. The area trapped between the graphs of f and g is calculated by the integral from A to B, and we look at the absolute value of the difference between f and g. I mean, we need to find which one is the bigger one, which one is smaller, and then we subtract the smaller from the bigger in order to get the area between them. The lovely exercises from high school were about functions that intersect 2 or 3 times, something like that, and we have to divide it to subsegments in which f is larger or g is larger and calculate the integral correspondingly. Now, generally speaking, it's just the absolute value of the distance between them. So it was an ASCII. I don't necessarily remember everything from high school, but it's enough for me. Just like talking about finding the extrema points and the inflection points of a function. Here at Israel, at least in high school, they are go all over go all over it. 1 year, 1 full year of just finding inflection points and something and stuff like that. So here in Infi, we don't have to do it all over again. So don't feeling any necessity of an example or something. Maybe near in practice, maybe in homework, just to feel it with our bare hands, but it's not very important from my point of view. Something similar. I personally did learn it in high school, but I don't know about you, so I write down more explicitly from high school again, maybe. The volume of a body of a revolution. Know what I'm talking about?
Yeah.
No? Yeah? Okay. Yeah, body of revolution. It's actually a very important concept in differential geometry. For you as a year A/year B students for computer science is not very important. So write it down as quickly as I can. We know the concept of body of revolution. No, we want to draw it with our. Let's for the simple example.
This is using more 3D frequent, right?
One can generally speak about, and we will discuss it in the end of our course, talking about the integrals of functions of more than one variable. But one can generally talk about the volume of any body of 3 dimensions. It's called a triple integral. It's very fun. But for computer science students, yet again, year A, year B, it's not very important. Calculating areas and volumes is very important to very big and open problems in computer science as well. For example, we have this building. It's three-dimensional building, and we want to cover it with sufficient Wi-Fi, for example. Okay. I had my 10 o'clock class. It's Infi 1 for Hebrew students. The Wi-Fi in the class just didn't work. So I used hotspot. But let's say I want to cover it with an efficient Wi-Fi, so I'm going to put the routers in some points. How do I do it efficiently? Where do I put the routers? I want to use the minimum number of routers needed, and where to put them? It's a big question, important. I want to cover Israel with gas stations in such way that, let's say, from every settlement, you have to drive maximum 10 kilometers for the next gas station. How do I cover it? Now, that's somewhat a two-dimensional problem. You look at the map and it's enough, but it's all the same. Covering problems, packing problems from the other side. In the building, I want to put total of 2,000 chairs for students. How do I divide it between the classes? That's called packing. Specifically talking about the body of revolution, not everybody's body of revolution, but specifically talking about the body of revolution, first of all, let's draw something. Let's say it's the function, I don't know, x squared or something like that. We can, first of all, we can rotate it around the y-axis, and we get some nice, I don't know, bowl. And on the other way, we can rotate it along the x-axis and get some nice, not a bowl, to not call it some mashpech in Hebrew, I don't know. There's a difference to bodies. And generally speaking, one can say, you know what, I have some two-dimensional domain and some line next to it, and I can spin the domain around the line and get a three-dimensional body. And one can talk about the volume of such body in the general case, but it requires some notions from physics, such as, you know, it's called Merkaz Koved, I know, mass center probably in English. We just want to remind you what we know about surface of revolution, the volume of such body from high school. So as usual, I'll paste it as a PNG so it will stay with us. And then I write down the formulas. I didn't. Okay, so first of all, let's put it here, but let's save the file itself. Hopefully it will not blow up. It is Infi2, lecture 7, by Allah. Yeah, going forward. Okay, and scale it so it won't blow up the PDF afterwards. 7 is good enough. When rotating the graph of f in the segment AB around the x-axis, the volume of the body of revolution we get is V, يعني volume, by the integral from A to B, f squared dx. Why is that? The formula is not very complicated question, but it does requires the understanding of the general concept of triple integrals, calculating integrals of three-dimensional bodies, which we don't know yet. So just write it down. And yet again, you probably saw it in high school. As far as I remember from my years in high school, it was a long time ago, not 80 years, but something like 18 years, yeah. They don't teach here the how do you calculate the area of the body of revolution around the y-axis. Let's write down the formula as well. If you know, if you don't, it doesn't really matter. Let's Control C and then Control V. When rotating the graph of f around the y-axis, the volume of the body of revolution we get is 2 pi and x fx. Have you seen this formula before? For the y-axis as well? Okay, nice. So in here as well. You can turn it the other way around. If you express x as an expression of y, then it will be the opposite. I mean, when you rotate it around the x-axis, it will be this one, and etc. Vice versa. Yeah. No, wait. In the boundaries of the integral?
Y. Yeah, because you're still doing it on the y-axis, you want it to be f of a and f of b, right?
So here, this is the formula from a to b when I multiply by x and 2 pi. If I express x as an expression of y, I can look at it from the other side. And this will be the f Baribua f squared y dy will be the volume of the body around the y-axis, and the same for the x-axis. But putting fa and fb in the limits of the integral, no, because it's not, I'm not using a substitution. I'm just looking at the expression y is some expression of x, and I just flag out x as an expression of y. I'm not putting in the integral itself, t is some expression of y or vice versa. If I use substitution to calculate an integral, I can write the limits as fa and fb, yeah.
But if you're doing it, you've got the x-axis, and you're doing it from point A to point B. If you're doing it on the y-axis in terms of x, and you're flipping it like that, and now you're going from height A to height, it's making sense.
Yes, but the price I pay is in the integral itself. It's not pi and f squared, it's 2 pi and x of x. And with these elements, the integral is from a to b, even though it's around the y-axis. And again, why is that so? You can ask it about the first formula as well. We need to know more about the general concept of triple integrals, which we don't know, or at least don't know yet. That was 2, right? Yeah. So the 3, which is, first of all, the most, I think, basic one, and I think for me, I'm going to teach you, the most important one is the arc length. You know, the area, oh, first of all, I want to say it without even writing it down, but a body, a three-dimensional body, has a volume, which is one of the basic geometric properties of it, characteristic aspects, whatever, but it does have as well a surface area. Yeah. So there is a formula using only one-dimensional integral as well to calculate the surface area of a body of revolution. I don't want to mention it here, but just for you know that it does exist. I do want to elaborate about the arc length. Arc length, that's what I write down. I think it is. Now it's a very basic question, yeah? I stated for continuously differentiable function. Let f be a continuously differentiable function, meaning that the derivative is continuous. That's continuously differentiable. Um, the length of the graph of f between the points A if A. Oh, yeah. A if A and B if B can be calculated by let's call it L, يعني length, the integral from A to B of the following weird expression, square root of x plus f tag squared. Now, as I started to say, area, okay, that's how we defined the different integral in the first place. So it's the first geometric use of an integral. But why go to the volume of revolution? Asking about the length is much more basic concept of geometric aspect. Okay, it's the length. It's a very natural question to ask. So if f is continuously differentiable, the length is can be calculated using this formula. Have you seen this in high school?
Uh, oh, so I don't remember most of high school already for 6 years ago.
Yeah, but then so for the example, as far as I remember, I didn't see it in high school as well. Now, what do I want to do? We have another half an hour. Is give you an example for this, calculating the arc length, and then I want to prove the formula is correct, which means that I need to formally define what a length is, as we did with the integral and the area. So first of all, let's start with an example. For example, we calculate the arc length of the function is hyperbolic cosinus. You know what this is? Cosine? Yeah, let's write it down explicitly. Exactly.
Yeah.
Average between e to x and e to minus x. Let's say in 0 and 1. Now the function itself is some function, and we need to calculate the arc length of the graph. Just for you to know, generally speaking, square root of 1 plus something squared is not so easily calculated. I mean, finding the antiderivative. Here you multiply by x. If f, for example, is sinus, so x multiplied by sinus, you use integration by parts, as we saw in the first lecture. But generally speaking about the arc length, you get not very nice integrals. So what you usually trying to do is finding some shtick in the function itself in order to cancel the square root. I mean, expressing the function as something squared and the square root is canceled. In our example, we have f tag x is, let's write it down.
That's what
No,
remember some. No, I'm talking about, I'm talking about
no. As far as I remember, no.
oh.
But it's just just a notation from my point of view. This is the function. And of course, the exponential function is widely discussed. We can all agree, doesn't matter how much do we do remember from high school, that comparing to what we do now, it is a big waste of time using all these, I don't know, 8 or 10 or 7, whatever hours of math every week. and you don't have a break between the semesters, you start at the 1 of September, you finish at the 1 for July or something. 10 months of every week, 8 to 10 math hours, and you accomplish almost nothing. It's a big waste of time. Right now, in our example, you have 0 and 1, and the derivative of f, we can write it down easily because we know how to derive e to the power of x. The minus just goes out. Now, we know how to calculate what's inside the square root. It's e to the power of 2x minus 2, e to the power of x, e to the power of minus x, and e to the power of minus 2x. That's above 4. להוריד לכם טובים. ex and e minus x cancel each other, leaving us with 2. And if we take the 1 and lift it up to the numerator, it becomes a 4. If I somehow wrong, you should correct me. 4 minus 2 is plus 2. And as far as I can see, this is the most we can get from opening the brackets, the parentheses, and stuff like that. And as I said before we started the example, in these kind of exercises, most of the time it's finding some trick or stick or whatever to cancel the square root. I mean, one can try to substitute t with the expression in the square root or with all the square root. We mentioned it when we talked about finding the derivatives in lecture number 2 and lecture number 3. And when you have an integral with square root, good start, it won't work all the time, of course, is to plug t as what's inside the root, or t is all the root itself, but it's not what's going to be here. As far as I can see, it won't work, but you can try. T is what inside the root, then dt is blah, blah, blah. As I said, the trick is to somehow cancel the square root, meaning that we need to write down the function inside the root as something squared. Now, as we already seen in the upper line, the opening of the brackets here gives us e to x minus 2 plus e minus 2x. Now, when we have plus 2, what does it mean? What do we actually have in the integral? One can write it down as, I mean, if you want to see it very clearly, you can add e to the power of x, e to the power of minus x. Another trick shafel in Hebrew. But it don't have to do it. It's the right place and right time to say that when it comes to algebraic mumbo jumbo, you can write fewer steps and you will be fine. We know that you know how to open parentheses and etc. etc. I'll rephrase it. It's not what I'm going to test you, yeah, examine, whatever. The course is not about opening brackets. But it is part of it, of the technical work. So when we close the parentheses, we get this nice, good little squared fella, which do cancel, which they do cancel each other, the square root and the power of 2. Moreover, the expression itself is always positive. It's e to the power of x. So we don't need to use the absolute value. We can just write it down like that. And um, when we calculate the integral here, it is an immediate integral, which is very nice. The integral of E, what? The integral of E is E. The integral of E minus x is E minus x. And we put x0 and x1. When you put 0 is 1 minus 1, which is 0. And when you put 1, you get E to the power of 1, which is E, minus E to the power of minus 1 above 2.
The way you do calculation when you don't calculate.
What again?
Like when you know hyperbolic, like hyperbolic trigonometry, like identity, the way you get calculated.
Yeah, but again, we don't be too afraid of it. They're like the trigonometric function, the hyperbolic function do have their own identities, such as sinus hyperbolic squared is 1 plus cosinus squared or something like that, and derivative of cosinus is sinus, and sinus is cosinus, etc., etc. I don't need to. One can forget the hyperbolic cosinus. Just write it down that way, and we'll be fine. We already read down if power of x and so on. Let's write down cosinus hyperbolic. That's his real name. Um, Another questions? Okay. So as I said, I want to use the rest of the time to prove why the formula is true. And we need, first of all, to define what a length actually is, and then show that when the function is continuously differentiable, it can be calculated using this formula. And I need to remind you some of the one of the theorems from in Phi1. There is another technical kind of exercises I wanted to talk about today, but with our more than 10 minutes delay, our usual delay, I don't think we're going to do it. It's not so bad because it's very technical and I leave it to Nir on the practice, which as far as I understand is very nice and you all go there and have very much fun. In order to prove the formula we just stated, we first need to define what the length is. I mean, the intuition is very clear. Okay, it's lines, left, we know what this is, but we need to formally define it in order to prove something about it. So, the definition, let's do it quickly, should be similar to the definition of the area we started to define in the end of lecture number 3. What did we do? Did we do there? We wanted to define the area beneath the graph, more specifically between the graph and the x-axis. And we used rectangles. We know how to calculate the area of a rectangle. And using the concept of partitions and limit, we use the total area of the rectangles to define the area itself. I want to do something similar with the length. So let's write down the definition is similar to the definition of the signed area we used when it comes to definite interval. Let's write down that way. So let's have a nice drawing. Again, let's write down an axis. We only need the x-axis. It is enough. Let's say it's the point A, and that's the point B. And we have the point A, FA here, and the graph goes like this, and then we have the point B, FB here. Let's say we want to calculate to find the length of this nice line. What kind of lines we do know how to calculate their length? Straight lines. Yes, segments. So one can choose some points along the segment and look at their images on the graph. Now we can write down the straight lines, straight segments between the points, and have us, in Hebrew we call it kav shavur, a broken line or something like that, of some segments that is an approximation for the length itself. And of course, if you, let's write it down with another color, if you add a point to the partition and you write down the corresponding segments, you will get a better approximation. Here, for example, the two red lines are a much better approximation for the length of the black line than the one lonely blue line. And the definition will be the same. You take a partition, when the parameter goes to 0, and if for every such sequence of partitions you have the same limit, it is the length of the function. So let's, first of all, paste a PNG of our very nice drawing, and then write down with words what I just said orally. Scale it as well. I don't know, it'd be 6.5. I think it's enough. So, if for every sequence of partitions PM with parameter, the parameters, the greatest length of subsegment goes to 0, the limit of the sum of the straight lines, that's all right, straight? Huh? Straight lines is the same, then the function has length. And this limit and that limit is the length of f. More precisely, what is if the partition PM contains the points x0, which is the left side of the segment, and x1 and x2, and so on and so on, till we have xn, which is b. It tells me that my internet connection is unstable. It's not my internet connection, it's the university's one. The z between a and b, the length of the line between the point xi minus 1, fxi minus 1 on the graph, and xi, fxi on the graph is, let's call it di. Di is, how do we write down the distance between 2 points of the straight line? I don't know if you remember or not, it's from the high school as well. So it's xi minus 1 squared, the difference between the x values squared and the difference between the y values squared as well. You can get it by Pythagoras if you insist. This is the I, and so we define LF to be the limit of the sum of the i's. Now, more precisely, L is defined when every limit does not matter the partitions you take, is the same. And as we did in lecture number 4, we gave an example for a function that does not have an area, the Dirichlet function. One can give a function without length, not just unbounded one, something more ugly, like the Dirichlet function, but it's not very important. I mean, the area is the definition of integral, and this is some of its geometric uses, so it is enough just to define formally, as we did right now, the concept of length. And what I want to do now, 10 minutes left, is to prove, or at least write some parts of the proof, why when f is continuously differentiable, we can calculate the length using this formula and not looking at some series of sequence of partitions and calculating the limit of the sum of the di's. For that, any questions about the definition of length? If you write down, you can have take a minute, and then we'll do it together. I remind you that after the lesson, not exactly, I have another lesson in Rishon, I drive, then at night, I turn it into a PDF, and it's on the Moodle, it's on the Lambda, and I send it to the WhatsApp group chat as well. So if you write down just to have it written down, you don't have to. It helps you to understand the material, it's something else. So, any questions? We need the definition of length. Okay, we define it. We need as well, now, we reminisce a nice theorem from the Lex from our last course in Phi1 with Erez. We now we are going to use Lagrange. That's what you write his name, I think. Lagrange's mean value theorem. If f is continuous in AB, the closed segment, and differentiable is differentiable in the open segment. It's not an important thing why here it is square and here it is a circle, because the whole concept of derivative is not defined in the edge point. It's the slope of the tangent line, and when in the end point you don't have tangent line, so formally written in the open interval. Hope you're okay. If f is continuous and differentiable, there is a point evap. Now will ask me, do you want to save it? No, but I will save the main file. There is a point C in AB such that the derivative in C is FB minus FA above B minus A. We're going to use Lagrange's theorem along the proof. So let's write down here. Don't get shocked. Now, for the proof itself. F is continuously differentiable, and we desire to show that the length of F, which is the limit of all the sums of the DI, whatever, can be calculated by this formula of this integral. So let's write down what L of F is actually is. One can write, let PM be a sequence of partitions with blah, blah, blah. I mean, I just control C and control V, so why wouldn't I do it? Why wouldn't I? So let PM be a sequence of partitions with lambda PM by definition of the limit, which we defined after the theorem itself, the formula itself. L is the limit of the sum of the DIs. And what is the DI? We have already written. It's this nice square root. Now, my goal is to express this limit of sum as the limit of sum of the Riemann sum of the function square root 1 plus blah, blah, yeah?
What is the notation of the
What?
What is the notation of the
The limit is where m goes to infinity. And the sigma is from all the points of the partition, from 1 to n.
Okay.
So what do I do? Some algebraic shticks. First of all, we can take the difference between xi and xi minus 1 as a common multiplier, and we have 1 plus the difference between the images above the difference between the x's themselves. Now, two things we can do, algebraically speaking. First of all, is taking this one out of the square root, which cancels its power of 2. Because xi is greater than xi minus 1, it is positive, so we don't need to use an absolute value when we do so. And secondly, if we do have a fraction where both the numerator and the denominator are squared, we can put the square all over the fraction. In Hebrew, I call it under one umbrella. But we have 1 plus, let's write it down that way, the difference between the images and difference between the x's themselves squared. And we plugged out the difference between the x's as well. It's outside the square root now. Now we wait. Okay. Now, why aren't you going? Now, for this kind of fraction, we can use the Lagrange mean value theorem. Now, by Lagrange, by Allah, there is some point ci in the segment between xi minus 1 and xi, such that this nice fraction is f tag ci. In addition, we know that the difference xi and xi minus minus 1, excuse me, is denoted by the delta of xi, or just delta I if you want. It's a big delta. So we get the length we started with is actually the limit of the sum of the square root of 1 plus f tag ci multiplied by, no, outside the square root of delta xi. Now, by the definition of the definite integral, because f tag is continuous, it's one of our conditions in the sentence, in the theorem. Continuous, we know that all this square root of 1 plus f tag squared is continuous as well. And we need to finish, but let's just finish the sentence and them. I take this part of the sentence and put it here, just to be more reasonable. By a definite integral, the limit of the sum is indeed the integral between a and b of the function square root of 1 plus f tag squared, because it is the limit of its Riemann sum. If that's right, Riemann. That's the Riemann sum, the value at some point ci multiplied by delta xi. That's what we call the Riemann sum since lecture number 4. And the limit of the Riemann sum, when the function is integrable, is the integral itself. So we use some algebraic shticks and Lagrange mean value theorem in order to express the limit of sum of the definition of the length as the limit of sum of the kind of Riemann sum. Now, it's not the Riemann sum of f. It's the Riemann sum, as we got, of the square root of 1 plus f tag squared. And now we will be finished. I don't want to linger any longer. Not you, not me, but one last sentence. From first look, it was enough to state that f tag is integrable. So this square root of 1 plus f tag squared will be integrable as well. But first of all, it's not that simple that if f is if tag is integrable, then this one is integrable as well. In lecture number 5, we state that if f and g are integrable, then the sum is integrable as well. It's simple. But square and square root and plus 1, it's not so simple. And secondly, it's not just a function. It's f tag. It's in the derivative of some other function. And as we mentioned Darboux theorem before, a derivative can be continuous or have one main singular point, which means the function is not bounded, and it's a complicated discussion. So as we already did in lecture number 6, we take maybe stronger conditions that we actually need to get these results. But with these conditions, the proofs are simple enough. And on the other hand, it is enough to solve any exercise that we expect you to solve. Okay. We already finished. Any questions? So there is, as I mentioned, another use for the definite integral and the theorems we